Scene 1, Recreation 1.
Hi there, it's me again. Welcome to the fourth episode of LIPPAD TV. Today, we will be discussing about the different plasma thrusters used in cube satellites. But first, what is plasma? Well, we all know that at 100 degrees Celsius, water evaporates from liquid to gas at atmospheric conditions. For certain substances, if we continue to apply heat to their gaseous form, another change of state could occur, the plasma. For the change of state to occur, very strong heat must be applied. This strips the electron from their respective atoms, creating free electrons and positive ions. The equal amounts of oppositely charged particles makes plasma neutral. Free electrons are present substances in plasma, which means it can conduct electricity. Naturally occurring plasma includes lightning and the northern lights. In everyday life, plasma can be found in fluorescent light bulbs and neon lights. But there's actually another use of plasma. It is utilized as thrusters for cube satellites. Now, how does this work? This is a cube satellite micropulsed plasma thruster, a 2-watt, 42 Newton-second impulse plasma thruster which weighs 280 grams. The thruster works by pulsing a lightning-like electric arc between two electrodes. This vaporizes the thruster propellant into charged plasma, which is then accelerated by the electromagnetic field set up between the electrodes. The thruster could serve as a CubeSat deorbiting device, gradually reducing the orbital altitude until atmospheric re-entry is achieved. There are different types of plasma thrusters, and for this video, we will be discussing 4 of them: the helicon, the pulsed, the metal, and the liquid-fed plasma thrusters. Now let's start with helicon plasma thrusters. The helicon plasma thruster ionizes the gas using an antenna that emits radio frequency. The radio frequency discharge is coupled into the plasma with the magnetic field that also acts as the magnetic nozzle to accelerate the plasma-producing thrust. Thanks to this electrode-less design, the system needs less components and becomes simpler, thus decreasing the manufacturing cost and paving way to a cost-efficient mass production of small satellites propulsion systems. Sometimes, spacecraft do unexpected things that you don't imagine just for them to navigate in space. And one of these things is actually vaporizing Teflon. And that's right, Teflon that you can find in your frying pans. And this is an example of a pulsed plasma thruster. To generate its plasma, PPTs eat Teflon. A Teflon block is placed between a pair of metal plates, then wires electrically charge up the metal plates until it arcs through the Teflon block, set off by a spark plug. The arc brings about 1,000 volts into the block, vaporizing the Teflon and ionizing it into a plasma. Everything in the thruster is already arranged so that the magnetic field caused by the electricity pushes the plasma out into space. At this point, the third law of Newton already springs into action, launching the spacecraft into the opposite direction of the departing plasma. So the third type of plasma thruster we're going to discuss is the metal plasma thruster, or the MPT. The MPT is a pulsed electric propulsion device that converts solid metal component into approximately a hot plasma that expands hydrodynamically into the vacuum, hereby generating thrust. An MPT works by applying a small voltage spike to the copper trigger sleeve, which causes the plasma to form and bridge the vacuum gap between the cathode and the anode grids. This seed plasma causes the cathode phase to generate cathode spots and ejects an ionized plasma of the cathode metal at high velocity toward the anode grid. Each cathode spot lasts for a certain amount of time, and when extinguished, creates another spot nearby. Over many firings, spots completely cover the cathode face, resulting in an average thrust that is normal to the cathode face and parallel to its axis. Now lastly, we have the liquid-fed plasma thrusters. Liquid propellants are now generally becoming more attractive than solid propellants due to its advantages. And plasma thrusters using liquid propellants are what we call as the liquid-fed plasma thrusters. They are generally known for its low contamination issues, controlled mass supply, and high efficiency. Using an intermittent ejector, liquid propellant is supplied into an inter-electrode region. A fraction of ejected liquid is vaporized into gas, and main discharge is initiated with a spontaneous discharge from an igniter. This converts liquid and gaseous propellant into plasma, where it is accelerated both electromagnetically and electrothermally and exhausted out of the thruster. Alright, so that ends our last video for our radiation transfer series. I hope you learned a lot. Thank you for watching. Don't forget to subscribe and click the like button.